In this video, we'll take a look at linear regulators. Linear regulators basically waste power. They waste that power as heat that goes into the environment for any excess voltage that we've got. So if our input voltage is much higher than our output voltage, we'll waste more power and generate more heat as a result. Now, if we can use this as a bit of a thought experiment of how it might look, well, the basic way of dropping one voltage down to a different voltage is using a voltage divider. Now, voltage divider, you've got two resistors and your output voltage is based on your input voltage and the ratio of those two resistors. Now, can we use that if we want to run something off this and supply power off it? Well, we can't. And there's two reasons why we can't. The first is our input voltage, our 12 volts or 9 volts or whatever it happens to be at the top there, might change over time. And so that's an issue for us. Our second problem, though, is our current taken by the device may also change over time. Sometimes it might draw milliamps, sometimes it might draw 100 milliamps. And so based on those changes that are happening, our voltage output is going to change because essentially that bottom section of the voltage divider is going to be changing correspondingly the voltage output that we're getting out of it. So obviously we can't just do a basic voltage divider. We can for signals. For example, if we've got a 5 volt signal and we want to drop it down to 3.3 volts, sure, we can use a voltage divider there because we've got a fixed input that we're feeding into that and our output is really drawing no current whatsoever, or should be drawing minimal current. So that's not a problem. So what do we need then? Well, we need some sort of a feedback loop that's going on there. And in that feedback loop, as our current changes, we can match our current or our output voltage against a reference voltage, and this is what we want. So that voltage divider will essentially be changing all the time, matching what we've purchased it to do, what output voltage that we actually want there. So here's a bit like what it looks like inside. So we've got our VREF there. Now that's our reference voltage that's being created via like an internal precision reference based on the output voltage or a divided down version of what that output voltage is going to be. So we're comparing that with a comparator and seeing whether the voltage that we're supplying out is greater than or less than that V reference. And based on that, we can turn on our transistor or our switching element there by a certain amount. If we need to increase the voltage, we can turn it on more. If we need to decrease the voltage, we can turn it on less. Now there's a bunch of different devices and we'll talk through some of them in a moment, but typically a lot of these linear regulators will have maybe 3 pins on them. Occasionally they'll have an on-off pin or something like that we can disable the regulator altogether. But it's essentially an input, an output, and a ground. Now a current amplifier there is driving the base of the transistor, and we see that we need a voltage drop across that transistor. That's VCE, and that voltage drop is where our power is dissipated. So whatever current we've got flowing through there, multiplied by the voltage drop across that particular transistor there, tells us how much power that we're actually wasting. The remaining voltage, which is VCC, will go out to our device. So we see here that with this feedback loop that we've got there, if our device draws different amounts of current, needs to draw more current for a little bit or less current for a little bit, or our voltage supply changes, or we have a higher voltage or a lower voltage, we can then keep on going and keep, with our feedback loop, supplying VCC as a stable amount. This will also help us realize why our input voltage needs to be higher than our output voltage, because we actually need that voltage drop to occur. Now you can see here that in the top here, one of these things in a little package, that we don't have a separate current amplifier and voltage reference and a transistor. All this is in one little package, and they typically have an input, an output, and a ground. So they're very easy to work with, very easy to connect up. Doing so, you need very little extra components. Typically, you might have a capacitor on the input and the output to smooth the voltages a little bit, but very, very little aside from that. And because we're not doing high frequency switching outside of this actual package, it decreases the electrical noise that we've got, so we don't have a whole lot of noise that's coupled onto our voltage lines. And they typically have pretty fast response because we've got this internal feedback loop inside a device that's going on. Now, around efficiency, linear regulators typically aren't known as highly efficient devices. It's not entirely true though, because when we're dropping a tiny little voltage across that transistor, they can actually be quite efficient. When we've got a large voltage across that transistor, well, the voltage, the efficiency goes to some sort of a terrible level where we're wasting huge amounts of power. So that's one thing to consider when we're looking at one of using these. How much voltage are we going to drop there? And that will directly impact the efficiency. Well, we have some disadvantages, obviously, and the efficiency is the first one. So switch mode is normally much higher. So for a linear, if you're dropping from 12 volts down to 3.3 volts, you're looking at 27.5%. For a buck regulator, you're looking at above 90%. And you've also got that concept of V in always being greater than V out. Now, for a boost regulator, for example, you don't need to have that. Now, it's useful to actually look at some data sheets for these things, particularly when we're designing with them. So one common device is the LM7805, which is a 5-volt fixed voltage regulator. You can also get adjustable ones, and we'll look at that in a moment. Now, if you look at the data sheet, you can see that the voltage input starts at 7 volts because you need a buffer there, otherwise the voltage will drop out on the output of 2 volts. So 7 volts up to 25 volts is the voltage input there. We can also see the minimum, the typical, and the maximum voltage that this will put out on the output pin, the regulated pin. And so you see there's a potential bit of ripple there. Generally, they're quite flat at 5.0 something volts. And they generally have quite a nice output there. We also see down the bottom that our dropout voltage is 2 volts, so we need at least 2 volts above our output voltage. And the peak current, so we're looking at 2.2 amps. And when we're running at that sort of current, these things can get quite hot, so you probably want to have heat sinks on them or some sort of active cooling there as well. Now, aside from having a fixed voltage one like this, we can also have an adjustable voltage one. In the adjustable voltage one, we basically have 2 resistors, and those 2 resistors form a voltage divider. Now, we can use a little potentiometer to adjust those 2 resistors, so you can turn it and get a different voltage output. And there's a couple of different versions of these that are quite popular. The LM317 that gives you up to 1.5 amps output, or the LM350 which gives you up to 3 amps output. So double the output there. And these can be handy because you can use them in any place you would use LM7805 or LM7808 or whatever those fixed ones are. You just need to use those resistors accordingly or tune it in to be that particular voltage there. They do, however, require a couple of extra components.